Hello everyone, welcome to another video lecture of Mathematics Solution channel, and today we are going to discuss about how to solve the RLC circuit. Suppose if you have any circuit, then how would you go about using circuit analysis technique to come up with the second order differential equation? Well, once if you come up with the second order differential equation, we want to put it in the standard form, and based on the standard form, we want to make what kind of time domain response was C, whether it is underdamped, overdamped or critically damped. Have the R circuit here. This is the input and resistance. We have inductance and capacitance. This voltage across the resistance denoted as VR, and voltage across the inductance is denoted as VL, and passing through the current passing through the capacitance, it is denoted as VC. In this particular example, we want to write the differential equation for voltage across the capacitor. In order to do that, I am going to use the Kirchhoff's voltage law. What is meant by Kirchhoff's voltage law? The sum of all the voltages is equal to 0. That is, here we have input, that is VIN, and current passing through the resistance, that is VR, and similarly the inductance and the capacitance is equal to 0. And I am going to rewrite this statement as VR plus VL plus VC is equal to VIN. And let us take equation number 1. Now the voltage across the resistance by Ohm's law, voltage across the resistance, that is VR, which is same as current times of the resistance. Now substitute this value here in the first equation. This will become I into R plus VL plus VC is equal to V into IN. And similarly, by Henry's law, the voltage across the inductance VL is equal to L into di by dt. This is the voltage drop here. Now substitute, let us take in this equation number 2. So this will become IR plus L into di by dt plus Vc is equal to Vin. Let us take number 3. Now by Faraday's law, the voltage across the capacitor, so I can be written as C into dVc divided by dt. Therefore, di by dt will become, which is equal to C into dVc divided by dt square, that is d square Vc divided by dt square. Substitute these two values in the third equation. You will get, that is CR into dVc divided by dt plus L here, L into C d square Vc divided by dt square plus Vc equal to the input. And now we have the second order differential equation, but this is not a standard form. In order to make the standard form, the highest order, the second order differential coefficient must be 1. So divide through to divide, it is LC. So this equation will become R by L into dVc divided by dt plus d square Vc divided by dt square plus Vc divided by LC is equal to Vin divided by LC. Now rewrite this equation. This will become d square Vc divided by dt square plus R over L dVc divided by dt plus Vc divided by LC is equal to divided by LC. Now the right hand side is called forcing function or electromotive force, that is not equal to 0. Suppose, just recall the differential equation solution. If you have the right hand side, that is called a particular integral or particular solution. If it is equal to 0, then we can call it as a homogeneous solution. If the homogeneous solution is, the factor is called a damping ratio. It is denoted as zeta. Is zeta, and here we have R over L. Therefore, R over L is equal to 2 zeta into omega n, and 1 over LC is called the natural frequency of this circuit. Natural frequency of this circuit, where if you go through L and C are the energy storing device, which is transform the energy from, that is inductance is transform the energy to the capacitor, and the capacitor is transform the energy back to the inductance. If R is equal to, that is resistance is equal to 0, then you will see the circuit will oscillate. That is 1 over LC is equal to omega n square. Now zeta determines how the particular circuit will behave in the time domain, whether it is overdamped, underdamped or critically damped. That all depends on the zeta value. If zeta is greater than 1, the circuit is overdamped, and if it is equal to 1, that is called critically damped, and if it is less than 1, the circuit is underdamped. And that's it for the RLC circuit. And finally, if you want to solve this second order differential equation, we have many methods, and one of the best method is by using the Laplacian equation. And if you like this video, please subscribe my channel for more updates, and thanks for watching.